Okay, in this lecture, let us discuss a few more points about FM generation. Um, okay, so we learnt that we could generate FM signals using different kinds of methods, namely mm, the direct method, right? And the second one is the indirect method. Okay, so we looked at the indirect method, namely Armstrong method. In the direct method, we had a voltage controlled oscillator method. Okay, so we looked at the Armstrong method and how it could be used in practice, especially for commercial applications. So the direct method cannot be used for the broadcast applications. Thus, the alternative method, that is the indirect method called the Armstrong method of FM generation, is used. We looked at a typical commercial example, that would be commercial design for an FM transmitter, in which we have to choose a narrowband FM first, and then initially we have to make a narrowband FM generator, okay, followed by frequency multiplier, and then you have frequency translator, and then later on we had again one more frequency multiplier. For frequency translator, I should have a local oscillator, okay, FLO. Therefore, the narrowband FM generator generates a signal with a small modulation index. Here the modulation index is much less than 1. So frequency multiplication produces FM signal of a wideband FM. So here you'll get a WB FM, wideband FM signal of a large modulation index. Here beta is greater than 1. So in this process, carrier frequency also gets multiplied, right? And to get the requisite carrier frequency, we may have to go through one or more stages of frequency multiplication, followed by this frequency translation. This is the frequency translation. So these are the things that we discussed in the last class. Now, what are the advantages of using this method? Okay, you may ask, why should we use this indirect method at all? Okay, after we have to go through so many stages of operations. So the main advantage is frequency stability. Frequency stability. Okay, now this may look a little odd because we are working with that is, we are talking about frequency modulation or phase modulation, right? So frequency and phase modulations are naturally associated with the variation of instantaneous frequency. So what do we mean by frequency stability here? Because after all, in your frequency modulation, the frequencies keep on changing depending upon your input signal, that is your modulating signal. But here we are saying that it has very high frequency stability. Okay, so your indirect method offers very high frequency stability. So that means whenever we have transmitter or anything that modulates the carrier, for various reasons, it is desirable that the carrier frequency remains unchanged, remains fixed. So what do we mean by remains fixed? Basically what we are saying to say here is that it does not drift with time. It does not drift with time. That's what we mean by frequency stability. All electronic components are subject to electronic drift. Electronic drift or thermal drift, right? So because of the temperature variations, there can be variations in the properties of the circuit. Okay, so there can be variations in the properties of the circuit, and one of the properties that one has to worry about in oscillators is the frequency of oscillation as a result of these drifts. For example, as I mentioned earlier, the frequency of oscillation is typically depend on the resonant circuit L and C, right? That is R, L, C components. So the RLC components themselves keep on varying if there is a temperature variation, and that leads to a drift in the frequency. That is center frequency of the oscillation, and that is not desirable in any electronic system. For example, if there is a significant frequency drift at the transmitter and your receiver doesn't know about it, okay, right, then the receiver will get affected. And there is so many millions of receivers, particularly in a broadcast communication channel, okay, in a broadcast situation. So it is very much desirable in many broadcast applications or communication applications to keep your frequency of operation fixed, and don't allow to drift too much. Okay, typically fixed frequency of oscillation requires high stable oscillators. Fixed frequency of oscillation requires high stable sources. Resonant frequency, and typically this comes from what is called a crystal oscillator. Generally, crystal oscillator provides a stable frequency. Okay, it is a stable source. So crystal oscillators which use a quartz crystal resonant circuit. Electrically, it can be modeled as a resonant circuit, that is a parallel resonant circuit. Crystal oscillators is a very stable source of oscillation. If you use a crystal in the tank circuit, that is parallel resonant circuit of an oscillator, it is a highly stable source. Now, once you start with a highly stable source like this, then there is no way you can change its frequency. Okay. So whereas in frequency modulation, what do you want? What do we require? A change in frequency. The frequency has to be changed. So these are contradictory requirements. You cannot use crystal oscillators at the same time have variation in frequency. Whereas in indirect method doesn't have this problem, right? In indirect method, we don't want we don't have this kind of problem, because our starting point is not FM generation at all, right? What is our starting point? Generating a narrowband FM signal. In the narrowband FM signal, this is more or like your AM signal, right? Narrowband FM signal is generated with the help of DSB-SC. For DSB-SC, you need only a stable oscillator, because your DSB-SC is multiplier and you have an oscillator. This oscillator is fixed frequency oscillator. Recall the block diagram of narrowband FM. Okay, so the DSB-SC modulator has the fixed local oscillator which is used by a multiplier, and the other input is M of t, message signal. Therefore, M of t is being multiplied by your fixed frequency oscillator. So therefore no direct variation of frequency is recorded in this case. The local oscillator which is producing sin omega ct or cos omega ct can come from a highly stable oscillator, for example the quartz crystal oscillator. So that's what I mean by this advantage, frequency stability in the indirect method. So the center frequency of the carrier is not subject to drift. So what is my center frequency? FC, and this one is not subject to drift. That's what we mean by highly stable circuit. Okay, so frequency stability is more. That's what we said here. Frequency stability. Okay, not subject to drift. It is highly stable. It can be made highly stable by making use of a crystal oscillator as the starting point. After that, you just multiply this frequency with m of t, you'll get a DSB SC. So instead of cosine omega ct, you start with sine omega ct, and then you put a 90-degree phase shift, and whatever you get here, you put a plus mark, and this one is minus and this one is plus, and you'll get the narrowband FM. So you are not doing further any generation of the center frequency. Once you produce a center frequency, that is fixed. That's it. So that is the main advantage of your indirect FM. Now we can ask you, what is the cons? Okay, what is the disadvantage? Is there a disadvantage? Okay, yes, there is a disadvantage. We will see what the disadvantage is. Okay, this we have discussed briefly earlier. The disadvantage is that the narrowband FM generation is based on an approximation of the actual FM signal, because we represented the actual FM signal as A times cosine of omega ct plus phi of t, right? Now you expand this in terms of quadrature components, cos omega ct and sin omega ct, then A times cos omega ct, cos A cos B, cos of phi of t, minus A times sin omega ct and sin of phi t. When phi t is much smaller than 1, I mean smaller than 2 pi, right? If phi of t is less than 2 pi, then there is an approximation involved in this equation. Let me call 1. Okay, and that approximation is quite good, right? What is the approximation we used? Cos of phi t is equal to 1, and sin of phi t is equal to phi of t. Now if you use this approximation, then you'll get A times cos of omega ct minus A times sin omega ct, you multiply by phi of t. A times phi of t sin of omega ct. Okay, that's it. Now if you recall, in the last lecture, we considered a voice or music, and we said the typical bandwidth is FM is, let's say, 50 hertz to 15,000 hertz, right? Now we assumed beta is equal to 0.5. I mean, if this is less than 2 pi, therefore we assumed this beta is equal to 0.5, produces what? Narrow band FM signal. Now how will I find out delta F in this case? I need to find out delta F. What is the relationship between beta and delta F? Beta is equal to delta F divided by FM. Now which FM should I choose? Should I choose 50 hertz or 15,000 hertz? That is the next question, right? In case, for the sake of argument, let me choose FM is equal to 15,000 hertz. Now what is your beta? Beta is given. What is the beta value? 0.5. And what is your delta F? We need to find out. What is your FM? 15,000. So this implies your delta F is equal to 7,500 hertz, right? Now delta f is equal to 7500 Hz. Now for this case, what is the beta for lower frequency? Let me call delta f divided by your FM. What is your FM lower frequency? 50 Hz. You bring this 50 Hz here, 50 Hz. So 7500 divided by 50. Now what will happen, your beta value now? This one will get cancelled, 155 and 5 times 75. It is how much? 50. Is it correct? No. 7500, right? 50. Yeah, that's right. 50 times. Therefore, beta is equal to 50. Now, for the sake of argument, if you choose the highest frequency component, then and this beta value is given, what is your delta f? 7500 Hz. Now use the 7500 Hz for lower frequency and calculate beta. Now beta becomes 50. But what is our assumption? Our assumption should be beta is much less than 2 pi or much less than 1. But here it is 50. So I cannot approximate my FM signal as a narrow band FM signal. See, for narrow band FM signal, this beta must be much less than 1 for all values of your modulating signal. That is the condition, right? This condition should be true for all values of message signal. All values in the sense what? All frequencies which are present in the message signal. I can say all frequencies present in the message signal. So that is why I did not choose the delta f value from the highest frequency component of your message signal. But if on the other hand, if you choose you take this guy for the sake of argument, let us take the lowest value. FM is equal to 50 Hz and beta is 0.5 given. Now what is your delta f? Delta f is equal to beta times FM. So in this case it is 25 Hz, delta Hz. Now what is the corresponding beta when the frequency is 15,000 Hz? In this case beta is equal to delta f by FM. Delta f just now we got 25 divided by your FM. What is your FM? 15,000 Hz. Now this is much less than 1 if you calculate 25 by 15,000. So therefore for the lower frequency for 50 Hz also your beta is less than 1. What is that value? We assumed 0.5. And for 15,000 Hz also your beta is much less than 1. Therefore for all range of frequencies in your message signal, your modulation index is less than 1. Therefore you can go for the approximation of your frequency modulated signal, that is your narrow band FM signal. Okay, now that is why we took del f by FM is equal to 0.5 and we found del f equal to 25 from the lower values of your message signal. Okay, so the reason why we chose it to be the lowest is because if we ensure that this del f by FM is small for the lowest frequency component, this will automatically imply that del f by FM or phi of t is much less than 1 for the larger values of the FM. So that is the point we need to remember. So that's what I mean by this advantage. So the center frequency of the carrier is not subject to drift. Okay, if it starts to drift, then we will be in under trouble. Okay, because we employed millions of receivers and all the receivers will suffer and they will not be able to demodulate your modulated signal. Therefore, it can be made highly stable by making use of a crystal oscillator as the starting point, because in the starting point we used a DSB-SE modulator. Okay, after that you just multiply the frequency, so you are not doing any further um, further generation of the center frequency. So that is the main advantage of your indirect method. Frequency stability is highly maintained. Okay, now what is the disadvantage? As I said, this we have discussed briefly earlier. The disadvantage is that the narrowband FM generation is based on the approximation of the actual FM signal, because we represented this expression based on the fact that your beta is, I mean your phi of t is much less than 1. Okay, now we are using quadrature carriers. Why is it called quadrature carriers? Because here I used sin omega ct, and here I am using cos omega ct, and here I am using sin omega ct. Okay, and here we are assuming 2 pi, actually it is not 1, let's say 2 pi, phi of t is much less than 2 pi. So there is an approximation involved in this expression, and this approximation is quite good if your phi of t is less than 2 pi. For example, if I consider the lower sideband, lowest value, then I'll get delta f is equal to 25, and use a same 25, and you calculate highest value, same 25, then it will be much less than 1. So that is the disadvantage. So as far as higher frequencies are concerned in the modulating signal, for those frequencies the approximation will be quite good, because what is the approximation? We took the approximation based on the fact that beta is much less than 1 or less than 2 pi. For highest frequency this is very less compared to 1 or compared to 2 pi. But for lowest frequency it is only 0.5. Therefore the approximation is not good for lowest frequency, and the approximation is quite good for highest frequency. See, for lowest frequency FM, what is your beta value? 0.5. Okay, for 50 Hertz. When FM becomes 15,000 Hertz, your beta is how much? 25 by 15,000. This value just you calculate by taking your calculator. Okay, so it's a very less value, less than 1. Okay, therefore for the lowest frequency beta is equal to 0.5. It gives poor approximation. If it is poor approximation, what is the problem? Let it be. Poor approximation leads to distortion. If you make poor approximation, then it will be like amplitude modulated signal. Okay, and that poor approximation leads to some kind of distortion. That is, the signal which you generate is not a pure FM signal. It is slightly distorted version of the pure FM signal. So you are not generating your FM signal like cos of omega ct plus phi of t. This you are not generating this directly. Okay, you are generating something that approximates this equation. Okay, you are generating something that approximates this FM equation, and that approximation is poor for low frequencies of m of t. Why? Because at low frequency your beta is 0.5. At high frequency your beta is 25 by 15,000, very less value. Therefore at high frequency the approximation is quite good, but for low frequency the approximation is not that much good. Approximation is poor. So if the approximation is poor, then that leads to distortion. Therefore this distortion will take the form of undesirable amplitude variations in the signal, which the original signal does not have. Okay, in the original signal you may not have this undesirable amplitude distortions, but the moment you do this kind of approximations, then your modulated signal will have some undesirable amplitude variations. Okay, so the original signal has constant amplitude. Look at here, this has a constant amplitude. But see, what is my original signal? x of t is equal to a times cos of omega ct plus phi of t. If you plot, then it has constant amplitude. It keep on changing with only frequency is changing, but amplitude is not changing. But if you take the approximated value of this, then it is going to be a cos omega ct minus a times phi of t sin omega ct. Okay, so in the original signal you have constant amplitude. In the approximated signal you have amplitude modulation, amplitude variations, so that you will not allow. If you make beta is much less than 1, then this amplitude variations will disappear. So the approximated signal, this is my approximated signal, will have some amplitude variations. So these are the pros and cons of using the indirect method. So at lower frequencies there is a slight problem, but otherwise it is a very good method, and this is extensively used almost in all commercial FM applications. Okay, so as against this indirect method, let us spend a little more time on the direct method. Okay, that I will discuss in the next lecture. Okay, therefore let me stop at this point. Thank you very much.